completely undescriptive title. But I guess what I'm going to talk about is a couple of small projects related to energetics and stability in locomotion. I had a big list of topics that I wanted to talk about, but I think what I'll talk about is the first two. So a lot of people talked about these big optimizations with musculoskeletal models or motor models. So I am doing some of them as well, but I'm not going to talk about that particularly. Maybe I'll briefly mention something about it, but these are a couple of other projects. Okay, it's work done by Leroy Long, who's a master's student at Ohio State. This is a graph that's familiar to most of us. This is the energy cost of walking, in particular energy per unit time, the total energy per unit time of walking as a function of speed. It increases something that looks quadratic, and running cost looks like that. Don't worry about the details of that, things intersect and things like that. It depends on which curve you use from the literature, and this is sort of composite. But suffice it to say that what we'll be using in this talk is the general shape of these curves, and in particular, there is some controversy whether the running cost curve is actually a straight line or slightly curved. I'll fudge this and say slightly curved, and the data can support really both, and really all we want is actually slightly curved. However, pretty slight is good enough. And I don't think the data is, the noise from the data is low enough that you can distinguish slightly curved from exactly straight. Okay? So people have done, since the 1980s or maybe even before that, people have done these sort of classic treadmill gait transition experiments in which you put a person on a treadmill, you start them out at a very low speed and slowly increase the speed of the treadmill. And there are various ways of increasing the speed of the treadmill. People either increase it, increase it, hold it, or slow continuous accelerations, all kinds of different protocols. They give slightly different results. So what the result being when people switch from walking to running, and then they decrease the speed again, people switch from running to walking, maybe at the same speed, maybe at a slightly different speed depending on the protocol. So there's a little bit of variability there. But it turns out that overall, people switch around this point, maybe a little bit lower. I think Preljak had a paper which said his subjects at least switched from walking to running at a speed about 0.1 or 0.2 meters per second, lower than the points at which the two curves cross when walking on a treadmill becomes more expensive than running on a treadmill. But other people have slightly conflicted data where the transition point is closer to that intersection point. In any case, so that's a classic treadmill gait transition experiment. And what does a treadmill do? A treadmill constrains speed, and in particular, short treadmill constrains speed, because if you fluctuate your speed too much, you will run off the front of the treadmill or fall off the back. So what happens to gait transition when you allow speed variations is the question that you want to think about. And essentially, you make the experiment a non-treadmill gait transition experiment. And this is the experiment. Let's say you want to get to the stop at 9:30, you're somewhere else, and you start at 9:30 minus t, and there's some distance that you have to cover, and you want to get from A to B, right? So there's a distance constraint and a time constraint. If you want to, not just the beginning of the talk. A distance constraint and a time constraint implies an average speed constraint. So d over t is constrained. So even though the speed at any point in time is not constrained, the average speed is constrained. Okay. Now, what should we do? What is the and what should we do? And the question, I'm going to interpret that question as what does energy optimality predict in this situation? And let me tell you what it predicts. So these are curves that look like so. It turns out that, so draw the common tangent between these two curves and take the point at which the common tangent touches the walking curve. Below that point, if the choice is between walking and running, what you should do is just walk. Above this point, what you should do is just run, and in between these two limits, what you should do is do a mixture of walking and running. That's what this theory predicts. So this is I don't know how old this result is, sort of mathematically. Well, even in the context of walking and running, there is this very obscure paper from 1986 in the Math Journal, which has this picture and this discussion. I learned this from a homework problem in a class that I took from Andy some 9 years ago. And the explanation is pretty straightforward. If you walk at this velocity for time t1, run at this velocity for time t2, depending on the t1 and t2, if t1 is 1, so to speak, you will pick this point out. If t2 is 1, you'll pick this point out. If t1 and t2 were half each or equal, your total cost would be on the straight line. Right, so it'd be some combination of these two costs. It would be on the straight line. So doing that mixture, half mixture of walking and running, would be better than doing all walking or all running. So that's why you should use a mixture in this regime. And this has to do with sort of this non-convexity for math folks of the sort of lower envelope of these two cost curves. Okay. You can generalize this result a little bit, tiny little bit, to include standing or resting in general. And if you say there is a resting cost, what you can do is draw a tangent from the resting cost to the walking curve and then draw this tangent. And then the predictions are that if your average speed required is below some quantity, what you should do is walk at some speed and then go stand at the end. So arrive early. If your average speed required is in some other regime, you should walk all the way and arrive exactly on time. If your average speed is a little bit higher, you should use walking and running, and then if the average speed is even higher, you should use all running. And these are the various fractions. Right? So all standing, standing and walking, walking and running. Right? Now we did an experiment. Leroy actually did the experiment, and we got a bunch of subjects, and we gave them the task of going from A to B. We gave them a stop clock, which is counting down, which prescribes the average speed by counting down, and we saw what fraction of walking and running they used, and we got this curve. This is the fraction of running used as a function of average speed, and you notice that, of course, they use mostly walking and mostly running, and then they use a mixture in between. It's understandable. We had sort of variants of that experiment. Indoor was slightly different from outdoor, and so on. We got a bunch of more. We measured a bunch of more things, but let me just skip through that. Is this a success or failure for the hypothesis of LHC optimality? We haven't worried about the actual numbers very carefully, but at least it captures the trends qualitatively. Because the actual numbers, well, depends on the curves and what numbers you use for the curves and so on. You have a bunch of other questions. What about the number of switches? Like we switch from walking to running a lot of times, or not just once in this regime. It's optimal to switch only once if there's this cost for the switch, but in our experiments, people switch only once. We could explore the dependence on distance. Ours is a relatively short distance, about 150 meters. And then are different people slightly different in terms of this transition regime, and it turns out that, well, we didn't find a very strong dependence on leg length, even though we had a somewhat substantial leg length range over about 30 subjects. Okay. Some crazy predictions. I wanted to give a second talk actually, but some crazy predictions from this sort of thinking about this. A child walking next to a parent, because its curves are shifted a little bit left to the parent, would tend to either lag behind or run forward, possibly. Maybe such same thing might happen for juveniles sort of migrating, say, with adult animals. If you have a dog on a long leash, maybe they might do something like this. These are all speculations, I guess. I'm going to speculate that this effect maybe is responsible for some animals at least not wanting to walk on treadmills when you put them on a treadmill and make the treadmill go slow, because the right thing to do is actually scoot on the sort of coast on the treadmill and then scoot forward and so on. right? And then you can sort of extend it to other things like moving walkway and things like that. And finally, another maybe crazy prediction, which I don't know if will ever come out in an experiment, is if you assume different resting states, and you say you have to get from A to B, and you get to either sit down or stand or lie down at the end, you would predict slightly different walking velocities. I guess I'll leave it at that. Looks like I've run out of time, should we go to questions?
So, Chris, you had suggested that the frequency of switches would be small, maybe just one. But it seems to me, and since I have some personal experience, because those of us who carry a little extra weight worry about this all the time, you have lung capacity issues, you have fatigue in your muscles, and as you run down the stores in those two compartments, then you want to take a break and restore them. So I actually run, walk with a very high frequency of switching.
I agree, right? So this does not take into account fatigue issue and things like that, and presumably, I think Andy tells me that I guess people have told me that there's a mythology about ultramarathoners doing a mixture of walking and running, and maybe it's because of this energy optimization, but maybe it's because of the effect that you're talking about, which is fatigue, which is not in this model. Yeah, I agree. Other questions?
I have one. So, have you thought about, or has anybody measured, and I realize that in this analysis, maybe the number of times you would switch would be negligible, but is there a significant metabolic cost in the switching compared to the steady state running?
Compared to steady state running, I guess not. I mean, because that, over any reasonable period of time, that would swamp the energy cost. But then there is the acceleration period, which is what gives the transition some cost. And yeah, so there's not a big cost, but it's there.
I remember there was an old guy that when I used to do cross country, he would go to the road races, and he would run and walk quite frequently. I mean, like 10 steps, 10 steps, 10 steps, and so then maybe the cost wouldn't be quite so overwhelming. I wondered if that was a good strategy. He seemed to be keeping up for an old guy, but I wondered if that was a good strategy.
Manoj, you mentioned a mixture of walking and running.
Yeah.
What's the speed you should choose for your walking and the speed you should choose for your running?
Oh, so the speeds are, well, okay, so that's, according to the simplest theory, the speed should be here and here. So what you should see is people walking slowly at this speed and running fast at the higher speed. Do people actually do that in the experiment? So that's these histograms were meant to try to pull that out, but the histograms unfortunately are pooled histograms, so they average a lot of subjects, which I should not have done. So any sort of double peak in the velocity histogram gets smooshed a little bit. But I don't know if that answers your question. But velocity, do you want the actual numbers for the velocity, or
I was just checking that it's the tangent points that would be
right, the other tangent points. Right.
Okay.
Yeah. Yes.
In biomechanics, there seems to be kind of a whole field of people studying the history of the transition.
Can you say it again?
There seems to be a lot of people in biomechanics that are really interested in the hysteresis and the transition.
Right.
And I never really understood what that was about. So,
In terms of an explanation, or the phenomenon exists?
well, I think for any system where there's some transition, it's not going to be too surprising that the transition isn't going to be exactly at the same place every single time. And so hysteresis or backlash or all sorts of things like that seem sort of inevitable to me. And so I'm just wondering, is there something fundamentally important about hysteresis, or is it just sort of an outcome of sloppiness?
It could be sloppiness. So the simple theory predicts, I mean, the simplest theory on a treadmill, if those curves were exactly true and you were exactly on a speed constraint, they don't predict hysteresis, right? But one can imagine sort of developing that cost curve into 2 dimensions where you say the cost is dependent on speed and step length. And let's say you have a walking minimum here and a running minimum here, and it might be that at some point there is both a walking minimum and a running minimum, right? So the two minima potentially. And it might be that you're tracking the walking minimum and you sort of overshoot until the walking minimum becomes not the local minimum anymore or something like that, and then you switch to the running minimum. So that's a possible explanation, which is exactly the same sort of mechanism by which you get hysteresis in all kinds of sort of mechanical systems with which sort of minimize potential energy, things like that. So same mechanism. Again, it has to do with this having 2 minima and sort of non-convection, things like that.
Can we please?
Well, I don't know if that's a real explanation or if the phenomenon is real. I don't know what's going on, but that's a potential explanation. And this is.
Thank you, Manoj.
Yeah.
Thank you. Please thank our speaker.